Okay, let's get started then with module 2, which is the overview and motivation. Why is testing important? What are the key terms and so on, so we can get into this. Um, so I have a few slides for you today, and then there's also links in this module to two materials. One is the online course, STTP, giving an introduction to testing. So that's one chapter in there, and then there is 7-8 pages that you can read in Fraser and Rochas, which is an introduction paper about software testing. So that gives a good introduction, a little bit more depth than the SCTP book. Okay, let's get into this. So again, model-based testing module 2. So the key things first to know, and you probably have heard this in other courses, but just to get us started here, we make a difference often between verification and validation. So verification is simpler. We assume in verification that we know requirements. So we have a very specific goal, and then verification is about checking whether the software we have built or the part of the software we have built is actually the right thing. So it follows from the goals, from the requirements that we have. Validation is very closely related. It also has to do with the quality of the software product, but in this, we sort of go outside of the requirements. So we don't confine ourselves to the goals and requirements and let them guide what is it that we're going to test or verify or validate, really. So validation is a broader term, so it's about, are we actually building the right product? So there are some testing activities that can be seen as validation. Often they include the customer or the final end user of the software, and you actually test with them as a sort of acceptance test or very final type of test that the product is actually fulfilling their needs, right? While verification would be more of part of the internal process where we try to ensure that the product fulfills the requirements and goals that we have written down or designed for and so on. So one example would be hacking wood. If you are hacking someone else's wood very fast, so you are churning out a lot of pieces of wood per minute, then you might be highly efficient. So you are building the product, right? So you're pushing out a lot of pieces of wood, but you're not being very effective. You're not building the right product. So validation would be about, are you actually, if your goal is to fill up on wood for the winter for your house, then you're not building the right product if you accidentally are actually hacking the wood of your neighbor, for example. And this is a sort of a simplistic analogy to how this can happen in developing software. I must say that in practice, in industry, often these things are blended together sometimes. So there will be quality related and testing related activities that can be seen as both, because maybe you as a developer or requirements analyst are sitting together with a customer. So even though the goal might be validation, you could be doing verification also in parallel in that activity. So in industry, I would say these blend together more often, but it is important to have this distinction in mind and to understand it. So, in scenario 1 here, if we look at a very simplistic sort of software development process where we go through requirements, design, implementation, and having some kind of end product, then one scenario is that we have actually done very good requirements engineering. So we have correct requirements. We have done a design that is in line with the requirements. We have implemented code which is in line with the design and thus fulfills the requirement, and the product works then as expected. This would be like an ideal classic sort of waterfall software development scenario 1. But actually what happens is more like scenario 4 on the bottom here. And of course scenario 2 and 3 are sort of in between. And in practice, you will always have a mix of these different things going wrong. But what is very frequent, of course, is that there are mistakes in requirements in engineering. So they are not complete. You have misunderstood something. You don't fully understand the end users. The end users have multiple different groups of them, so it's hard to cater to all of them in the requirements that you write and so on. So there are, in total, they are not perfect, right? There are mistakes in the requirements. Then, even if you had perfect requirements, your design will actually, okay, so this one actually, the design meets the requirements and the implementation meets the design, but the product will not match the user's requirements. So scenario 4. So I thought scenario 4 was with everything going wrong, but scenario 3 then would be that even though you could have correct enough requirements, you have made mistakes in the design. So even if you implement the design, the product has design flaws. And scenario 2 would be, okay, correct requirements, design meets the requirements, but you implement it correctly, so you have your code has bugs, right? But in practice, there will be mistakes in every step along the way, and you're going to have verification and validation steps throughout to try to weed down and filter out these mistakes in all of the different steps. Okay, some key terms that we need to keep in mind here, and unfortunately there are different sets, different uses of these terms, but I will show you two ones so that you know both of them. The one that is most used in the material we will use in the STTP book, for example, is that humans make mistakes. So we make errors while coding, while analyzing requirements, while doing the design. And this leads to defects, so bugs in common language, but we typically say that defects in some artifacts. So this could be in the requirements, it could be in the code, in the design, in the documentation, in lots of different artifacts. There can be defects, and some of them are more severe, others are more obscure and hard to sort of activate, but when some of these defects that are in the artifacts are activated during use, that is a failure, right? So the running software gets some data from a surrounding system, or there's some action input from a user, and that activates then the defect. And it has an effect, which is then the failure. So these are a common way to talk about a chain of events. So there are mistakes or errors by humans leads to defects in the artifacts, which during execution leads to a failure of the software. Right. But in the area of software reliability, there's something called a fault error failure chain. And there the terms are used in a slightly different way. So I want to mention them both because sometimes you might hear either of them used. So here we talk about a fault in an artifact. So the fault here would be more corresponding to defect in the other chain we discussed before. The fault leads to an error in the data during execution, right? So the error is the erroneous value of a variable or the erroneous update of a database. That is the error in the data during execution, and this in turn leads to a failure. So this is more focused on the latter two stages in the previous chain, but I mentioned them since the error term here is used slightly differently. So the error is either referring to the human error, the mistake that happened by the team or by a human during development, or it can refer to an error in the data, in the values of the data during the execution of a program. And then you see also that fault and defect and bug can somehow refer to a similar notion. Okay, If we look at verification and validation, there are two main groups of techniques. So static techniques, they do not require you to execute the software. So this can be code inspection, doing reviews, inspecting the design. Walkthroughs is when you have, say, the designer of the software sitting in a group setting, going through how they designed the software and getting feedback or criticism from others. It can be source code analysis. So source code analysis, you have some software tool that takes source code files and analyze them and try to find problems with them. So this is all static. So static refers to the software is not being executed. So dynamic techniques, on the other hand, they require execution of the software, right? So some artifact of the software is being executed. And, mainly it is the binary, the compiled software system, but it can also be some kind of model that you've developed and that you run. Then you can claim that this is still a dynamic technique, but it's done on a precursor, on an earlier step to the software. So in some sense, it's not running on the executable. So for more advanced techniques, these again, some techniques will be both static and dynamic, and combined hybrid approaches exist. But it's important to have this in mind that also in validation, you can have dynamic techniques, which would be like you sit the acceptance test. So the end user sits with the final system and uses it, right? And validates, yes, this is helpful for me. This is what I wanted. A static validation technique can be that you sit with the end users and go through requirements, right? So you try to weed out problems in requirements, but you're not executing the software. And of course, for verification, there are many examples of both static and dynamic. And testing is sort of the quintessential, the typical dynamic verification technique mainly, right? But it can be used also for validation. So why do we need testing? Well, one main aspect is economics. So, there will always be mistakes in software. No software is ultimately perfect and perfect for all time, right? So if things go wrong, it can be very costly. There are many examples. And part of the quiz for this module is that you will look into a few software disasters and look at the economics. So when a rocket blows up because of a software error, this is going to be extremely costly, both in time, resources, and money spent to fix, right? So this is a major source of why we need testing. But more seriously, of course, they can be devastating consequences. So people can die, right? This happens. I mean, some of the more famous software disasters that you can find when Googling for this is in medicine, where the software and the design of the interface of a piece of software for controlling dangerous equipment in healthcare was wrong or buggy and led to devastating failures where people got basically were killed by the machine because there was a bug in the software. So, this is so safety critical, robustness aspects for reliability and so on. We must try to weed down and get away with majority of the serious problems in our software. There's also PR, marketing, and market issues. So we will be embarrassed as a company if our software fails, right? So we might lose customers. If we have a lot of serious disasters or problems with our software, this will be picked up by society, by media, and of course this will have can have devastating, long-lasting economic impacts. So for PR, marketing, and so on, and I can say from my experience working with software companies in Sweden and in Europe and elsewhere, it can be very sensitive for them to share data about their faults and failures and testing, because they don't want PR or media to pick up and write articles about their internal quality processes. That can be a PR problem, a marketing problem. Then there are certification reasons for why we test. So the customers and the government forces us to do some testing. This is very common. I worked with the space industry, and there you have very harsh standards that you must fulfill, and they force you to do certain types of testing. For example, many of the standards force you to test so that you get full code coverage, that every line of the code will be covered. So for certifications, and this goes not only for space, many other industries, aeroplanes, cars, medicine, and so on. Increasingly, as software matures and goes into society, it becomes more and more important with certification. And testing is often sort of a prime part of quality assurance in such standards. Then we test because others use it. And so it's been around. It's sort of the most basic verification and validation technique. So most used technique in industry is also sort of easiest to get started with in many senses, in many ways. So many more advanced and formal verification and validation techniques require much more from you as a user, as a company, while testing is a lower barrier of entry, so you can get started with it. Yes, it's good to know about testing because it has been traditionally overlooked. So in the early days of software industry, companies wanted to churn out more software. They didn't put as much focus on quality and testing. So it was traditionally overlooked, so you can get a job in it. And there are ethical issues here also. As engineers, we take pride in our work, and we should, right? And testing is a critical part of ensuring that we release high quality stuff into the world. So there are ethical dimensions. So there are many reasons. A prime reason that we must do it is because the world and the software we build are complex, right? So fundamental problem here is that the software itself is so complex these days. It's developed in multiple languages, it's super large, it's very hard for individual people to know all of these systems and the software. And also our requirements are complex. We want software that helps us do very complex stuff. And these parts and systems, they are all complex individually, and then when they interact and inside the software when parts interact, it becomes very hard to predict everything that will happen in every situation. So even though formal methods and sort of more static ways of ensuring quality of software are important, I would say that they are also fundamentally limited, right? Because full predictability is extremely hard and costly to achieve, right? If you want full predictability of your software in every situation, you need to understand every situation, and you need to be able to have models and information and artifacts early on in your development so that you can predict exactly what the software will do. And this is going to be too costly. So testing will always be there, even though if we come up with new ways of doing verification and validation, we will still very likely complement them also with testing. So it is a very fundamental verification and validation technique. So what is it then? Yes, testing in general is to systematically experiment with some object that you want to assess or evaluate. And the goal is to evaluate its quality. So there are like clearly two parts to testing, two goals. One is evaluate, validate that the behavior, verify that the behavior is correct, and discover faults. So discover when it's not fulfilling what we wanted to do and weed those out, take those out, so that we can ensure and keep on ensuring, validating, verifying the behavior. So, software testing then is this systematic experimentation of a piece of software. So, evaluating the software, running it, observing its execution in different ways, right? Two main types, of course, manual testing. This is still used a lot in industry. It's often ad hoc, so based on experience or intuition of the developer, of the tester. This is extremely important, and it's not in any way bad. We should develop our intuition and our experience about software so that we can do good manual testing. There are also specific techniques or ways of doing manual testing called exploratory testing. And we can discuss that later in the course, but basically it's a little bit more structure to the type of manual testing you do, and you sort of document what you've done, and you can build on that and so on. And this is quite common nowadays. It became a phenomenon, let's say 10, 15 years back, and it's been growing in importance. But then a lot of testing, and especially testing research, is focused on automation, automated testing. So scripted testing, model-based testing, and many more recent techniques that we will study in this course. What are the main problems? Well, the input space is huge. So the input space, the space of possible inputs to a piece of software is astronomically big, right? It's super, super big. So we cannot test every input. This is a major problem. But also often is that the output space might be very huge. So, so even if we cannot test the input space, because that's very, very large. Imagine the input space for Microsoft Word is the space of all possible documents that you can write in Word. This is a very large space. So that's very hard. But even if we look at the output space, that might be very large also, right? So even if we say, oh, we can never cover the input space, at least we would like to cover the main types of outputs we can have. Like maybe printing from Microsoft Word is one type of output. Saving to file is another type. Even that space is very, very large in most cases. So we cannot really cover them, right? So we need to be smart. We need to motivate. We need to think of how we select and do the coverage of these two different spaces in a smart way. And then, of course, the mapping here between inputs and outputs can be very complex. And you have, of course, state in the system itself. So even if we give the same input multiple times, the output might be different because the state has changed. So the behavior of the system can often be very complex. And then, of course, as we said before, the specification is never fully understood. I mean, it's so costly to understand exactly what the requirements are in every situation for every possible end user that we can only approximate it. So we're never going to fully understand it. So testing is about validation, it's about verification, and if we don't fully know what we're trying to achieve, in some sense, it's impossible, right? So this makes testing hard. It's a main problem. How much information about the requirements and specification do we need to order to improve our testing, how to take the next step in our testing? Then, of course, testing is context and domain dependent. So it's not enough, even if you're a great software tester with lots of experience, you don't know everything about the domain where the software is going to be used, right? So it's going to be hard for you, even if you're an expert. If you come to a new domain, if you switch from the car industry to the medicine domain, it will be harder for you to be a good tester because you need to understand that domain, understand the context. How is my software being used in the hospital, right? So this also makes it harder. And even if we spend lots of money on specification, it's only a theory in a sense, right? All the type of modeling we do early on or write extensive requirements, documents, and so on. It's not until we have an executable system that we can actually see how it behaves. So We can do all kinds of static things early on in the process, but we will still have the same or related types of problems in the testing. I mean, we can weed out some problems with the static techniques early on, but we still need the testing, and it's not, we cannot assume that we fully understand the specification or the requirements. Then a little bit more subtle are psychological problems. So there's a lack of understanding the problem. There can be negative views about what testing can achieve. Testing can be sometimes be seen as not as creative as designing or coding, and then its importance might be lower by managers, and so there's a lot of problems with testing comes from like psychological problems in companies, in teams, and so on. So this is not something we're going to focus on, but we'll probably discuss it more later on. So what is now model-based testing? We're coming to the end, sorry, if it's of this lecture video. So model-based testing is then a specific type of testing. It's very often about test automation. And the general idea is that we build a model of some part of the system, right? It can be a model of the inputs, it can be a model of the outputs, it can be a model of the function of the system as a whole, some subsystem. But we build some kind of model, which is some kind of structure that we use so that we can then generate a lot of test cases automatically or partly automatically, semi-automatically from that model and run them on the system that we are testing. So you can argue that model-based testing can be manual, but 99% of the time people assume and will think about model-based testing as being a form of automated testing. Although we can do it manually, we can go through the same steps, of course. But one of the main benefits is that because we are investing now in building up a model of the system, of some aspect of the system, we want to use that a lot to generate a lot of test cases. So this is the basic idea. Because we are investing in this model, we want that to be good enough for our use, and then we want to be able to generate a lot of test cases from that. And one thing to note here is that traditionally model-based testing has been UML type of models. So some kind of modeling of the system, some subsystem, how they interact, what kind of messages are sent, and so on. But there are many types of models that can be used, and we want to have a broad notion in this course. So model-based testing can be on different levels. So often also you don't have only a single model. You do model-based testing and you have different models for different aspects, and you generate maybe different types of tests from them, or combine even tests by using multiple models. So we can model different things: data input, expected responses, output, the environment around the test, the structure of the system, and so on. So why model-based testing? Yes, we can do, if we have a good model, we can do thorough, better, deeper testing with it. It's more systematic because we can use the model to try to cover the model so that we then cover the important cases when we test. It can save costs if we can put in one day to develop a model, which we then can use during several years to do good testing. This can be cost saving, but it depends, right? If we have to spend a lot of time and change how we develop the software in order to build a model, then the trade-off in cost saving is harder to assess. It can provide automated traceability, so when we identify problems, we can go back to the model and see what does that mean in terms of the model, what aspect can be wrong. We can also ensure maybe that we can make claims that since we covered the testing of the model, we should have covered more important aspects of the system. So it can help us trace how good our testing is and how well it is traced back to the requirements and the design. It can help us for earlier detection of mistakes and defects because we are building often these models earlier in the development process. We can also use them to earlier find problems. We can use them to document test cases, and also over time when we update the software, and then this can help during maintenance of test cases and test suites. Okay, so summarizing today, there's a difference between verification and validation. Verification is about building the product right according to our goals, specification, and requirements. Validation is a wider issue about is this software actually helping the end users? We talked about motivation for conducting different types of verification and validation and testing activities, and there are many different types of motivation. We talked a little bit about the terminology, so you've seen a few key terms. We talked about fault, error, failure chain, and the error, defect, and failure chains. We talked a little bit about the structure of the area, but I will come back more to this, of course. And let's get this course started. And I hope to see you today on Wednesday for the first live Q&A session. Thank you very much.